Hello, and thank you for this opportunity to present our work. The title of my talk is Destroying Fault Invariant with Randomization, which was based on a CHES 2014 paper, a joint work with my two former students, Harshal and Shikha. A brief introduction about myself. I am Devdi Mukhopadhyay, working as a professor at the Department of Computer Science and Engineering, Secured Embedded Architecture Laboratory, with a focus on embedded security and side channel attacks. Here is a brief outline of my talk. I will start with the background, followed with the summary on the CHES 2014 contributions, and then the detail some of the technical aspects of the works and conclude with impact of our work. We all know that faults are extremely crucial in the context of cryptographic implementations, and faults can be used to recover the secret key. It was first conceived in 1996 by Monet, Demille, and Lipton, followed by interesting works from Beham and Shamid of developing what are called as differential fault analysis or DFA for block ciphers like DES. Today there are numerous examples of fault analysis of block ciphers. There's AES with a variety of fault models and fault injection techniques like clock glitches, voltage glitches, EM, and optical mechanisms. So here is an illustration of DFA. So DFA works on the analysis of fault-free ciphertext and faulty ciphertext, both operating on the same plain text and trying to recover the secret key. So the central block cipher that we discuss, that we experiment our work on is the AES algorithm. We know the AES is a standard from around 2000-2001 for block ciphers. The AES is made up of several rounds. In particular, AES 128 has got 10 rounds. Each of the rounds are made of substitution boxes, which are achieved by what are called as sub-bytes, followed by diffusion layers like shift rows, mixed columns. The last round of AES does not have the mixed column operation. So after the standardization of AES, there were several works which are done on developing DFA for AES. One of the notable works was due to Piret, which showed that two faults were uniquely able to retrieve the key with a time complexity of 2 power of 40. Now there were several following works which showed that there are two faults which are required for uniquely retrieving the key of the AES algorithm with a time complexity of 2 power of 32. Now there was in 2011, it showed that there was a work which showed that there is only one single fault which is required to recover the AES 128 key with a time complexity of 2 power of 30. In order to protect against these attacks, there were several countermeasures which are also proposed against DFA. The countermeasures can be broadly classified into what are called as detection-based countermeasures, which are based on application of classical fault-tolerant techniques to cryptography, and it uses various forms of redundancy. On the other hand, there are techniques which are called as infective countermeasures, which tries to disturb the information of a fault by infection, and there is no explicit detection step. So here is an illustration of the infective countermeasure. So there are two rounds, cipher rounds and redundant rounds, which are copies of each other. In case of then there is no fault, then both of them have got the same state. But if there is a fault, then there is a difference between them, which is picked up by a diffusion layer, and the diffusion is used to infect the output of the cipher round and the redundant round to render the ciphertext non-exploitable. It may be emphasized that these techniques avoid an explicit detection step by carefully embedding it in the infection process. So the CHES 2014 work is targeted a Latin Crypt 2012 infective countermeasure, which was based upon a cipher round, redundant round, and dummy round. The idea was that if there is a fault injected, then the subsequent rounds gets infected to stop or protect against for any fault attacks. In FDTC 2013, there was an attack which was targeted on these infective countermeasures. However, the attack assumed unrealistic fault models like constant fault models, and even showed that there were some serious limitations of doing the attacks, and also required a large number of faults. So this can wrongly throw a notion that the countermeasures are secure. However, in order to make, in 2014, we made a closer look at this countermeasure, and we exposed serious design flaws in the original infective countermeasure, which actually leads to attacks even with practical fault models like random faults. We also tried to use these findings to develop or construct an improved infective countermeasure that resisted all the known differential fault attacks. So here is the neck-to-neck comparison of our attack with the original attack in FDTC 2013. While the original attack required a constant byte fault model and was restricted to only the last 3 rounds of the 10th round, our attack works for any row position using constant byte fault model. It does not require or does not, while the original attack does not work for random fault models and therefore makes it kind of resistant against several class of DFA, we show that the original countermeasure is vulnerable to even random fault based attacks. While the original attack required around 36 faults and had a 2 power of 32 search time, we show that the entire 128 key can be recovered in only 8 faults. So here is a comparison of the final countermeasure against the original countermeasure. While the original countermeasure infects bytes with interrelated values, which can be used to remove the infection, we try to infect all the bytes with random values. And therefore, while the original countermeasure was vulnerable to attacks even with random faults, our countermeasure was able to resist all known forms of DFA with popular fault models. We tried to also make our countermeasure more unpredictable by introducing random number of dummy rounds after the last round of the encryption. So here are more technical details. So here is the pseudocode of the original infective countermeasure. I would try to kind of emphasize on the fact that there are 3 registers R0 and R1 storing the redundant state and the cipher round, whereas there is a dummy round which is also introduced here and is stored in the register R2. So the infective countermeasure proceeds by a sequence of redundant and the cipher round as shown here in this diagram. But in order to confuse the attacker, there are also dummy rounds, and the dummy rounds have got dummy sub-byte, shift rows, and mixed columns, and they are side channel leakage-wise equivalent with the other rounds to confuse the adversary. So how does the infection spread? So in the spirit of infective countermeasure, it takes the XOR of the redundant and the cipher round and is pumped into the diffusion function, which is achieved by a Boolean function, which is called as SNLF. So the SNLF is based on a Galois field finite field inverse, which means that if the input is 0, it produces 0 output. Whereas if there is a non-zero difference, that means there is a fault, then this is used to further infect the cipher rounds. It may be noted that this check happens only when we are computing the cipher round and not during when we are computing the redundant round. So the cipher round gets infected because if there is a non-zero difference, then that propagates further. The dummy round is also infected further. For example, you can see that the output of the SNLF is used to also infect the dummy round. And the dummy rounds, as we have mentioned, is essentially composed of dummy sub-byte, shift rows, mixed columns. It also has got another important point to be mentioned, that if there is a secret input beta and there is an idempotent key K0, such that if the dummy round is applied, then it results in the same value of beta. So in case of a fault in the redundant or the dummy or the cipher round, then since the SNLA produces a non-zero difference, the dummy round state does not remain beta. In fact, even if the fault is in the dummy round, then also the state doesn't remain a beta. So what is the consequence of this? So there is a further XORing of the dummy round with beta. So therefore, when the dummy round state changes from beta, then the XOR results in a non-zero output, which is used to further infect the redundant rounds and the cipher rounds. One final point is that in the description is that there is a final compulsory dummy round at the end. So that is shown here by this equation. So this round function is standing for the dummy round. It may be noted that if there is no fault, then R2, which is the dummy round state, retains the value of beta, and therefore this XORs with beta to get 0, and therefore there is no infection. Whereas if there is a fault previously, then R2 has already changed from the value of beta, and therefore now there is a further infection of the cipher round. So the FDTC 2013 attack was as is shown here, and it targets the last 3 rows with constant fault. In this particular slide, we show here where the fault is infecting the first byte of the second row, and because of the countermeasure, this will infect the fault computation twice, after the execution of the 10th cipher round and after the execution of the compulsory dummy round. So how does the infection take place? So because of this fault and because of the round function, this fault will propagate and further infect the cipher round by infusing a difference of which is the output of the SNLF function. It will also affect the dummy round, and the dummy round, because of the fact that there is a corresponding shift row and the mixed column, will result in a vector which is noted here as delta 1, delta 2, and delta 3, and delta 4, which will try to kind of infect the further the cipher round. However, because of the shift row, it can be observed here that the difference that we observe in the XOR of the faulty ciphertext and the correct ciphertext, as shown here in this slide, we can observe that the value of the epsilons or epsilon f epsilon is now exposed to the attacker, and therefore the infection becomes ineffective. So what the attacker can now do is that it can try to take this differential and relate it with the secret state of the cipher and use it to get one of the key bytes shown here as K1311. Likewise, if the fault is in the other 3 rows, the attack will still work, and therefore the attack will be able to recover any key which is in the last 3 rows. However, the attack requires like for every key byte recovery, it requires further three fault inductions or fault injections, but each of the time the fault value has to remain the same, and therefore the attack works on what is called as a constant fault model, which largely which makes the attack quite impractical. So why does the attack fail? First of all, when the fault is in the top row, as shown here now, the fault is in the top row, and again considering similar discussions as we have just now considered, we can observe that now the vector that is produced by the dummy round is shown here as alpha 1, alpha 2, alpha 3, and alpha 4. However, because of the fact that now we are considering that the fault is in the first row, and we know that in the first row there is no shift row, and therefore this value of this vector masks the value of epsilon XORed with SNLF epsilon, and therefore this value of epsilon is not anymore exposed to the adversary. However, we observed a major flaw in the infective countermeasure scheme, and that is shown here in the in the slide. So therefore, when you consider the fact that the dummy round is basically has got an input beta and has got an idempotent key K0, which results in the value of beta. So therefore, the infection because of the dummy round can be written here as shown here. And because of the fact that the mixed column and the shift row are linear operations, one can bring them out. And therefore, the infection is basically because of the fact of that the S of beta, which is the result of applying the S box on the unknown beta value, XORed with the result of the S box applied on the state or the current state of the dummy round. So how can we use it to follow what infection is being produced by the dummy round is shown here. So remember that now if the fault is in the first row in the and the first row of the value of R2 XORed with beta, then because of the round function, because of the fact that there will be an S box that will get converted into some value of Y, but because of the fact that there is no shift row, it will remain in that location, and there will be a mixed column which will result in interrelated differences shown here as 2y, y, and 3y. So what is the consequence of this? Again, let us look back at our attack slide. So if the fault is now in the top row, and remember that as I mentioned previously is alpha 1, alpha 2, alpha 3, and alpha 4. But because of this discussion that we have just now considered, we will see that the alpha 1, alpha 2, and alpha 3, and alpha 4 are not really random, but there is an interrelation between them. And therefore, although the value of epsilon or XORed with SNL epsilon is being masked by them, we can remove the masks by the fact that the attacker has the value of Y, and therefore with the value of Y, it can also calculate 2y and again obtain back epsilon XORed, epsilon, and can again perform the similar attack. So therefore, we show that the dummy round infects, but with interrelated values, and therefore it can be removed. So the more important consequence of this is that now we can extend this attack to work even with random faults. So for example, consider that there is a random fault which has been injected in any of the bytes, say now at the input of the 9th cipher round, and because of the property of the countermeasure, this will infect the faulty computation thrice. So note that we are now kind of ignoring or we are making an assumption that there is no dummy round after this fault injection except the final compulsory dummy round. So later on we will remove this assumption. So therefore there are 3 times the fault is affecting once after the execution of the 9th cipher round, followed by the execution of the 10th cipher round, followed by the execution of the compulsory dummy round. So here is a step-by-step explanation of how the diffusion spreads. Now, because of the 9th cipher round, this difference will now, because of the mixed column in the 9th cipher round, this will propagate in the first column, and that will again infect the corresponding cipher round by the output of the SNLF functions, and therefore it will get XORed with SNLF A, SNLF B, SNLF C, and SNLF D. Again, this will also affect the dummy round. Remember, the dummy round initially had a value of beta as shown here, but because of the diffusion of the output of the SNLF function, the first column will get affected. Subsequent to this, the 10th cipher round will get infected, and remember that initially it was in the first column, but because of the shift row, this will propagate to all of the columns, and that will again further infect the output of the cipher because of the diffusion function SNLF. There will be also a diffusion because of this onto the dummy round, and the dummy round state will now get infected and will have a state as shown here. It may be noted that like some of the bytes essentially will still remain their original beta values, whereas the other ones will be significantly different from the initial beta values. So what is the consequence of this can be observed here in the final dummy round infection. So the final dummy down infection using the property that we have just now discussed is that we can now consider the S of R2 XORed with S of beta, and therefore we can obtain this differential and observe how it propagates because of the shift row and the mixed column. So this is shown here below, and you can see here that this is the final infection that has been created, which essentially tries to mask the differential of the faulty and the correct ciphertext. So the consequence of this is now, while the attacker wants to obtain the values of M0, M1, M2, and M3, which are the actual differentials which are related to the secret key, but since they are masked and it makes apparently look like the attack is more difficult, but one can observe the differentials and can solve them to get the values of F1 and F2, for example, in the first column, and accordingly get the value of M0. Likewise, one can obtain the value of M3 and of F3 and get the value of M3. And likewise, one can also obtain the values of M2 and M1. Once the values of M0, M1, and M2 and M3 are observed, then we can see that there are around, for every correct cipher state like T, there are 2 power of 4 solutions for differential T star. And if you observe another pair, then you can uniquely retrieve 1 key quartet. And likewise, as we know in AES 128, there are 4 AES key quartets. So overall, we require 2 into 4, that is 8 faulty ciphertext to retrieve the entire secret key of the AES algorithm. So now let us assume that, as we have initially assumed, that there is no dummy round after the 9th cipher round and the 10th cipher round. But if you relax this assumption and assume that there can be dummy rounds, so what we want is the first favorable case where we are targeting the 9th cipher round by our fault injections. But otherwise, there can also be the cases 2 and cases 3 and cases 4, which can also occur, which are not really the good cases for our attack. How can we distinguish the good faulty injections from the faulty injections can be observed here, as we have observed that there is a special differential property in the correct, when we are doing our good fault injection, then one can use it to kind of identify whether the fault injection was really done at the appropriate location. But what is the probability that we will get the favorable cases among the unfavorable cases? One can work out simple combinatorics to find out that probability is 0.26, which is significantly large. And therefore, here is a simulation showing that the number of dummy rounds, when increased even to something like 30, we will get an average number of faulty encryptions around 300, showing that the attack works with around 300 faults to recover the entire 128-bit key of AES algorithm. So we looked into the flaws of the countermeasure. So some of the flaws that we found out was largely based on the fact that that although we were infecting the output bytes, but the infection technique itself was leaking, and therefore we needed to develop a mechanism so that the countermeasure itself is not vulnerable to this class of fault attacks. So in order to do that, we developed this methodology by using a random string which is called as an RSTR, which is a T-bit random string, out of which there are 2 n bits which are for corresponding to the cipher round and the redundant round, which means T minus 2n corresponds to the dummy round. So now what we allow is that the dummy round can occur at any location, and that means that the penultimate round is not really the cipher round, but there can be significant number of dummy rounds even after the final cipher round has been completed. We introduce a Boolean function BLFNF, which is a Boolean function which maps all 120-bit non-zero values or inputs to 1. And if the input is 0, then it results in a 0 output. So using this, we constructed a countermeasure, which is shown here. Let me explain this by considering the case when there is a correct computation. When there is a correct computation, then the BLFN produces a 0 output, and that essentially allows the cipher to propagate to the output, and therefore the output gets the correct output. Whereas if there is a faulty computation, then the BLFN results in a gamma value of 1, and that stops the cipher to propagate to the output, but rather the XOR with beta and the dummy round, which is essentially shown here, is propagated to the output, and therefore the adversary gets a random output, and therefore it is not able to use it for recovering the key. So the impact of our work can be identified by the fact that there were several works following this of of exercises to make and break, which is extremely important to assess the security of the of the countermeasure. There were around 50 citations of our work. We also extend our work in space 15 by analyzing it further, and that also had received around 46 citations. There were around 3.3 downloads of our work being cited in top venues like DAC, Host, Chess, TIFFs, Asia Crypt, and so on. So there were some works to analyze our countermeasure against first order DFA. In space 2015, we proved information theoretically that our countermeasure is secured. There were leakage assessments done in 2019 against various class of fault attacks. In 2020, it was theoretically shown to be secured against intermediate-oriented single fault attacks. There were works of applying several attacks or rather advanced attacks. For example, in COSET 2016, there was a note on instruction skips, but prior to that, in 2015, we had also extended our countermeasure and made it robust against instruction skips. There was works in 2018 chest of developing what are called as Cipher, and we showed that thousands of faults are required to break our countermeasure. And in Asia Crypt 2018, it was shown that the number of faults required increases quadratically with the dummy rounds. So here is an experimental validation that we presented in HAS in 2017 by showing a microblaze implementation of our countermeasure on a SSMOW board, and it shows that even several classes of attacks are countered. The number of faults are significantly increased, and also the instruction skip attacks are really being prevented at different frequencies of operation. In DAC 2019, there was an assessment which was done to show that many of the claims that we made in our original paper were indeed true, like protections against one byte secure attacks and single instruction skips and multiple instruction skips. There were techniques which was shown to subvert this countermeasure with two equal faults. But in our SPACE 2015 work, we also showed that the probability of such a two equal fault decreases drastically with the increase of in the number of dummy rounds. In chess 2018, there was an attack which is called as Cipher, which was tried to which was demonstrated on our countermeasure, but it showed that with significant with sufficient amount of dummy rounds, say the number of faulty encryptions required were of the order of around 50,000, which in a way also shows the resistance of the countermeasure against several advanced forms of fault attacks. So here are some reference of our work, and thank you for the attention. I will be very happy to address any questions.